Okay, in this video, we begin our studies of limits where x is approaching either infinity or negative infinity. To start with, let's consider the function f of x equals 2x. From the graph, we see that as x approaches infinity, meaning as x moves further and further to the right, 2x moves further and further up, approaching infinity. Hence, the limit as x approaches infinity of 2x equals infinity. We can make the same conclusion without resorting to the graph by thinking about what happens as we multiply larger and larger numbers by 2. The results will be growing larger and larger and approach infinity. Okay? Similarly, as x approaches negative infinity, or as x moves further and further left in the picture, 2x moves further and further down, approaching negative infinity. So this limit is negative infinity. Now, when evaluating limits, we usually plug whatever x is approaching into the function. If we do that for this first limit statement, and if we plug in infinity for x, we will get that this is 2 times infinity. And since the actual limit is infinity, we will get that 2 times infinity is infinity. Similarly, with this limit statement, plug in negative infinity for x, and we can sort of read this as saying 2 times negative infinity equals negative infinity. All right, let's do a similar analysis with the function f of x equals x squared. From the graph, as x moves further and further right towards infinity, x squared moves upwards towards infinity. So the limit as x approaches infinity of x squared is infinity. And from this limit statement, we can kind of read it as saying infinity squared is infinity. Similarly, as x moves left towards negative infinity, x squared moves upwards towards infinity. So this limit is infinity, and we can read it as saying negative infinity squared would be positive infinity. Okay, so here are some rules for working with infinities in limits. So earlier we saw how 2 times infinity is infinity. More generally, any positive number times infinity will be infinity. On the other hand, a negative number times infinity will be negative infinity. That makes sense because when you multiply a negative with a positive, the result should be negative. We saw how infinity squared is infinity, and negative infinity squared is also infinity. You can generalize that, so infinity cubed is infinity. Note that negative infinity cubed is negative infinity because when you cube a negative number, the result remains negative. You can keep going with this. I've listed a couple more rules, and there's, of course, more that I haven't written down. All of these rules can be reasoned by looking at graphs or by thinking analytically about them. So for instance, let's just take a look at this one here. The square root of infinity is infinity. So why would that be the case? When we square root larger and larger numbers. The results, though smaller than the original numbers, the results are still going to grow without bound and approach infinity. So that's why square root of infinity can still be considered infinity. All right. Now, there's one important rule when working with infinities that I did not include in the above list because I wanted to single it out. Let's consider these limits as x approaches infinity and negative infinity of 1 over x. From the graph, we can see that as x approaches infinity, 1 over x will be approaching the y value of 0. Hence, the limit as x approaches infinity of 1 over x is 0. Likewise, as x approaches negative infinity, 1 over x also approaches 0. So both of these limits are 0. Again, you can also think analytically about these and not look at the graph. For instance, imagine what happens as we divide 1 by larger and larger numbers. The results get smaller and smaller and approach 0. All right. Now from these two limits, if we plug in infinity for x, what we will get from these two limits is that 1 over infinity is 0. And the second limit, when we plug in negative infinity for x, we could read it as saying negative 1 over infinity is also 0. More generally, any finite number over infinity can be considered equal to 0. And so this is a very important rule. This rule allows us to evaluate the limit as x approaches infinity or negative infinity of any rational function. A rational function being a function which is a ratio of two polynomials. Okay? So I will illustrate this with a few examples in the next video. So that's something to look forward to. I want to end this video by looking at a few other expressions involving infinity. In the context of working with limits, each of these is an indeterminate form. There might be more on the list as well. It would take too long to go through all of them right now, and we're not going to need them for the future videos that I have planned, though you will encounter them in your calculus courses. So I will just focus on explaining one of them. Let's try to understand why 0 times infinity is an indeterminate form. So let's consider two simple examples. Let's look at the limit as x approaches infinity of 1 over x times x. And then also the limit as x approaches infinity of 2 over x times x. Looking at the first limit, if we plug in infinity for x, we're going to get 1 over infinity times infinity. And since 1 over infinity is 0, as discussed earlier, this looks like a 0 times infinity situation. Same for the second limit. Plug in infinity for x. Again, any finite number over infinity can be considered equal to 0. So this looks like we're getting 0 times infinity. However, in the actual limits, clearly we can just cancel the x's out. So this would just be the limit as x approaches infinity of 1. And 1 is just a constant, so as x goes to infinity, 1 is just going to always remain 1. So the limit is 1. And similarly, the limit as x approaches infinity of 2 over x times x, after you cancel out the x's, it will just be equal to 2. So the first 0 times infinity that we have up here appears to be equal to 1, whereas the second 0 times infinity up here appears to be equal to 2. This illustrates how, when working with limits, 0 times infinity can really be anything, and this is why it is an indeterminate form. We cannot determine the value of the limit by observing that it approaches 0 times infinity. This often seems confusing to some people because 0 times anything is always 0. What's important to realize in these examples, though, is that we're not actually multiplying 0 times a number. Rather, we are multiplying something that is approaching 0 with something that is approaching infinity, and we're asking what the result of the product approaches. And here we're saying that the result of the product could really approach anything. 1, 2. Of course, if I change the number 2 to any other number, I would get a different answer. Okay? So that's why 0 times infinity is indeterminate. You can apply a similar reasoning to everything here as well. All right, that's it for this video. In the next video, we're going to see how to evaluate limits as x approaches plus or minus infinity of any rational function. Thanks for watching.